Hello everybody. Today we're going to be talking about surface integrals. Now on the screen here you have this coordinate system, the x and y z plane, and what I have drawn on here is just a small snippet of a surface. And with this given surface, what I did was I then cut the surface, or I then constrained the surface to show me some domain. Alright, so any point that I choose on this domain will then reflect onto that surface there. Now, the reason I want to do this is because we're going to start defining what a surface integral is. So, on the definition on the screen here, you're going to see that it says, let z equal g of xy be a function that represents a surface S. The surface integral for S is given by, and that's going to be this double integral over this specific surface, right, which we denote with S, for this function f of x, y, z with respect to the surface. Alright, so notice the notation here. We're going to have to be very careful when we're working with that notation. So the notation here says that this ds, we are working with a surface integral. So this is going to be equal to the double integral over the domain that is restricting that surface. When we do that, we have to go through and we have to make our substitutions for what we know. What's x, what is y, and what is z. Now, notice again that z, well, we already defined z to be g of xy. Therefore, my insertion here just turns out to be g of xy. But also notice that we're also going to multiply by this radical. The radical of the partial of my function g, which is again defined by the surface with respect to x, square that, plus the partial derivative for g with respect to y squared plus 1. And again, this is going to be with respect to the area, in which the domain exists in. Now, we did go through this parametrization of surfaces, and the parametrization of surfaces says that if we have a surface given in R space 3, then we can go ahead and we can parametrize using two different variables. We'll call them u's and v's. And that's going to be the second definition that I have below here. That if we choose a parametrization for the surface using vector notation, where we have u and v existing in some domain, then the surface integral looks very, very similar to what we had up here. The only difference is that we're going to parametrize, or we're going to make our substitutions in our function, in our integrand, for our values that we found with our parametrization. And then we're going to multiply by the magnitude of the normal vector, or the magnitude of the cross product of that parametrization, and that's going to be with respect to the area. So notice that these two formulas are identical to one another. One chooses the parametrization, one does it with a parametrization of the surface, the other one does it in more of an explicit form. And so when we're doing this, we have those two different options. Can we choose to parametrize a surface, or can we just do it explicitly? Typically, if you want to parametrize a surface, it's because it's some sort of a circular domain, or we're going to be integrating a double integral in polar coordinates, or something like that. So we have to be very careful with that. Secondly, for the first definition here, for this first definition, we chose our function to be g of xy, and that was going to be equal to z. Well, if we would have chosen a different function, say if this would have been x is equal to g of yz, then that changes our insertion, or that changes our values for this double integral. Even though it's still going to get us the exact same integral at the very end, the exact same value, we have to be very careful. And that's why we go through the whole process in chapter 15 in knowing when to choose which domain. Alright, is it a type 1 integral? Is it type 2? Is it type 3? What type of integral is it? So, if you were with me from chapter 15, well, in chapter 15 we talked about double integrals and triple integrals and double integrals, and we always identified the domain first before we started setting them up. Specifically because once we get to these sections with surface integrals, we always want to identify what is the domain that we want to be integrating over, and then after that we can set our functions to be what we need. Alright, so let me give you a quick analysis of how all of this is going to play out when we're talking about these surface integrals, more of a visual on GeoGebra. Alright, so follow me along to GeoGebra, please. Alright, so here's my example on GeoGebra. So I have this one surface in RSpace 3 here, and when I'm looking at what domain I want to be identifying, typically we want to go with X and Y because that's what we feel more comfortable with. So if I were looking at an X and Y domain for this particular for this particular surface, then the domain would just be the unit circle. However, if I start looking at the domain in, let's say, the YZ coordinates, then my domain doesn't exactly turn into that circular domain. My domain turns into this particular piece here. Alright, so we have to then be very, very careful as to how we want to portray this domain and how we want to analyze this domain. Alright, in which coordinate system do we want to analyze it? Now, when you saw the definition for the surface integrals, notice that if I was looking at a parametrization of this surface, then I just take the cross product, the magnitude of the cross product of its partial derivatives. But in the first definition where we didn't parameterize, where we kept it explicitly, I multiplied that integral by the square root of the partial derivatives of the surface. Wouldn't that stand to reason that it's just the magnitude of the gradient? Alright, so think about what the gradient is for the surface, and then once you find that gradient, take the magnitude of that gradient. It should be that exact same value that we were observing in that first definition for the integral. Which means what we're going to be able to do here is once we have a surface, we're going to need to find its gradient, or in other words, its normal vector, and then we're going to have to go through and integrate over the magnitude of that normal vector at all times. Alright, so that's what we're doing here in this particular section. So now that we see this more visually, let's go back and let's start working on an example in class. Alright, so here's going to be your first example. We're going to have here this example that says evaluate this surface integral for 6xy ds, where s is the portion of the plane x plus y plus z is equal to 1 that lies in the first octant and in front of the yz plane. Alright, so there's a lot of information being given to us here. Number one, we want to find a surface integral. Number two, we're given a plane, the equation of a plane. And number three, we're given the specifics of the region that we want to observe. Now, because they're giving us the specifics of what we want to observe, they're actually giving us that this is going to be in front of the YZ plane. So naturally, because they're telling me that it's going to be in front of the YZ plane, chances are I want to use that as my domain. So I want to use that as my domain, which is going to be the YZ plane. Now, if I'm going to be using the YZ plane as my domain, I'm going to go through really quickly and I'm going to draw my axes here to reflect that I'm going to have a YZ domain or a YZ plane. Alright, so I'm just getting this Y and Z plane going here. There we are. And again, we know it's in the first octant. which means on the YZ plane, it's going to be in the first quadrant. All right, there we are. Looking pretty good so far. All right, let's go through and let's put some increments on here. All right, there we are. Now, since it's in the first octant and on the YZ plane, well, if it's on the YZ plane, I'm going to be using the fact that x must be 0 in order to be on that YZ plane. So if x is 0, then I'm going to use the equation that was given to me, that x plus y plus z is equal to 1, and I'm going to make that substitution of 0 into my equation so I can extract what I'm looking at. Now the equation is going to be negative y plus 1, which means I have a z-intercept at 1, slope is negative 1, so I go down 1 over 1. Here we are. Oops. Alright, and then here's going to be my line. There we are. So this equation of this line is z is equal to negative y plus 1. And the region that I want to be looking at, or the domain that I'm going to be integrating over, that region D, is going to be this region right in here. Awesome. Alright, it's looking good so far. Now, once I have this, I can then go through and I can start saying, okay, well, now that I know this, I can start trying to set up my double integral for this surface integral. All right, and that's going to be this piece right over here. Now I scrolled a little bit downward, that way you guys can see what I'm looking at up here. This is the formula that I want to use for my surface integral. Now, because my domain is this triangular domain, or this specific plane that is given to me, I don't want to use a parametrization. I want to use just the explicit form, which is going to be in terms of x, y's, and z's. Given that, I can now go through and I can start modifying what my surface integral is going to look like. Alright, so let's look at that quick modification here. Alright, it's going to be the surface integral for 6xy ds, and this is going to be the double integral over the region D that I have here, and this is going to be for, let's say, 6. I don't have an x value, so I'm going to leave the x value kind of in green because I need to do something with it. Notice my domain is y's and z's, but I have an x in here in my integrand, so I have to alleviate that somehow. Alright, and then I'm going to multiply by the square root of the normal vector to that region. Alright, so what is that going to look like then? Well, that's going to look like 1 plus g, and I'm going to take the derivative with respect to y, square it, plus my function g, whatever I find to parameterize that, whatever I find for my function to reflect that surface, will then be the partial derivative of that function g with respect to z squared, and this is going to be dA, but that dA is really going to reflect the area within the y and z coordinates. So again, now I have some work to do. I need to find this function g. So let's go through and let's try to identify what is my function g going to look like. Well, I'm going to use that equation of the plane that was given to me. I'm going to use x plus y plus z is equal to 1. And what I'm going to do here is I'm going to solve for x. And the reason I'm solving for x here is because now I have a function, and this is going to be my function g, in terms of y and z. And if I have a function in terms of y and z, then that means I have my function in terms of the domain that I want to observe, which means I now have a value that I can substitute in for that x value in here. So I no longer need that placeholder, which is nice. So now I want to do is I want to find these derivatives. What is the derivative with respect to x for this function? Or sorry, not x, my apologies. What is the derivative with respect to y for this function, which is going to be -1? The derivative with respect to z, that's going to be -1 as well. Which now means that on this double integral, I now have 6 times, I'm going to make my substitution for my x value, which is 1 minus y minus z. There we are. And then this is going to be multiplied by the y value. Again, that's this y value. And then multiplied by the square root of 1 squared plus -1 squared. -1 was that partial. Plus -1 squared, that other partial. There we are. And then this is going to be integrated over that region. Now I can go through and I can start setting up my integral. We can go dz dy or dy dz, whatever we choose. Alright, now typically I like to take vertical heights first. So for me it would be a dz then a dy. So I am going to go dz dy. You can feel free to go dy dz, perfectly fine. Alright, so since I went dz dy, what I want to do now is I want to take these vertical heights here, and I want to find what is that vertical height here. So it extends from z is equal to 0 all the way up to z is equal to -y plus 1. So we extend from 0 up until -y plus 1. And then after we take those vertical heights, those horizontal values are allowed to change on the y values from 0 to 1. So they're allowed to change there from 0 to 1. Nice. Now all I have to do is evaluate this integral here. So let's go through and let's evaluate that. Alright, 6 is a constant, and then I'm going to have square root of 3. So I have 6 square root of 3 being a constant, integral from 0 to 1, and then integral from 0 to, let's say, -y plus 1. And then this y value is going to distribute, so we're going to have y minus y squared minus zy, and that's going to be dz dy. There we are. Which means this is a double integral that we now want to evaluate. So what I want you to do is I want you to then take time and evaluate this double integral. So if you want to put pause on the video, go ahead and pause the video and evaluate this double integral. I will give you the answer, but again, I want you to try to solve this double integral on your own. Alright? So the answer that we see here should be root 3 divided by 4. It's not a bad answer. Alright, so this is how we're using these this is how we're using these surface integrals. And again, you have to pay attention to what is being given to you and how it is being given to you. We always go with the notation for the surface integrals with that differential being ds. So now that we have this first example, let's see if we can go through and we can do a different example. So let's work with this example here. We want to evaluate the surface integral for z ds, where s is the upper half of a sphere of radius 2. Alright, so now what we have here is we want to find this surface integral, but the surface here is going to be the upper half of this sphere. Now, because they're giving us that the upper half of the sphere is that surface that we're going to be observing, then what I naturally want to do is I want to naturally parametrize this using spherical coordinates. So we want to parametrize. Use spherical parametrization. Now, again, please be careful with this. Because we're using a spherical parametrization doesn't mean that we're using spherical coordinates. A spherical parametrization just means that we're going to get a representation for the surface in terms of what we know to be spherical coordinates. But again, we are not doing a triple integral within those spherical coordinates. We're just using the parametrization to help us find what needs to be those values. Alright, so we know that we have a radius, or sorry, a sphere of radius 2. So I'm going to go through and I'm going to really quickly just write my spherical coordinates here, or my spherical parametrization. I'm going to have rho multiplied by, excuse me here, sine of phi cosine theta. Y is going to be rho sine phi sine theta, and z is going to be rho times cosine of phi. But what we're given is that radius is 2, which means we automatically get the x coordinate to be 2 sine phi cosine theta. We get the y value to be 2 sine phi sine theta, and we get z to be 2 cosine phi. There we are. So it's looking pretty good so far. Alright. Now, once I have this parametrization, I'm going to go through and I'm going to say, okay, my parametrization here, my r, is going to have two different variables. We have theta and we have phi, so I'm just going to do theta phi in this particular case. I'm going to keep it like that. If you want, you can make these using these, and that's perfectly fine. Alright, so here goes my parametrization that I'm going to be looking at. My x coordinate is going to be 2 sine phi cosine theta. Y coordinate is now 2 sine phi sine theta. And the z coordinate is 2 cosine phi. There we are. So what I need now are partial derivatives. So I'm going to go through my partial derivatives really quickly here. So my partial derivative with respect, let me go back here, with respect to theta here, partial derivative with respect to theta, that's going to be negative 2 sine phi sine theta, 2 sine phi cosine theta, and the next one's going to be 0. And then I have my partial derivative with respect to phi, which is going to be 2 cosine phi cosine theta, 2 cosine phi sine theta, and finally negative 2 sine phi. There we are. Alright, so this is what I'm looking at when I'm looking at my partial derivatives for r of theta and r of phi. Now, what I need to do is I need to find this normal vector, that way I can find that magnitude of that normal vector. So what I need to do at this point in time is I need to take the cross product for these partial derivatives. So let's go through and let's take that cross product for these partial derivatives. I'm going to have the I coordinate, which is going to be negative 2 sine phi sine theta. Then it's going to be 2 cosine phi cosine theta. Then the j coordinate is going to be 2 sine phi cosine theta, and then 2 cosine phi sine theta. And the k coordinate is going to be 0 and -2 sine phi. So in the I coordinates for this cross product, we're going to have -4 sine squared phi cosine theta. Alright, minus 0, so that goes away. Minus the j coordinates. J coordinate, that's going to be positive 4, and that's going to be sine squared phi sine theta. There we are, minus 0 once again. And then the k coordinate, so plus the k coordinate here. That's then going to be 4. Let's say -4. And let's see, sine phi cosine phi sine squared theta minus 4. And that's going to be cosine squared. So sine phi cosine phi and then cosine squared theta. There we are. Alright, so let's go through and let's try to simplify as much as we can before we move on. So simplifying as much as I can before I move on, let's see, I'm going to put this back into component form. So this is going to be -4 sine squared phi cosine theta. The middle component, the j component, is going to be -4 sine squared phi sine theta. And the last component, notice that we can factor out a -4 sine phi cosine phi from both components, and that's going to leave us with sine squared plus cosine squared theta, which is going to be a Pythagorean identity of 1, which naturally just means that my last component should be -4 sine phi cosine phi, as such. So there's our last component. Alright, awesome. Now I need to find the magnitude of that component. So let's find the magnitude of that component now. So magnitude of r of theta cross r of phi. Forgot to put little arrows up here. There we go. Alright, let's find that magnitude. Alright, first component squared. That's going to get me 16 sine to the 4th phi cosine squared theta, plus middle component squared, another 16 sine squared, excuse me. So again, I'm squaring each component. That's going to be sine to the 4th phi sine squared theta. And the last component, again, 16 sine squared phi cosine squared phi. All of this is under a square root, as such. There we are. Alright, so yes, you all said it. We can factor out a 16, so we don't have to worry about that 16. That's just going to be the 4. Alright, because the square root of 16 is 4. And then what we're left with in here, we got sine phi, sine to the 4th phi, sine to the 4th phi in both of these first terms. So we're going to factor those sine to the 4th phi's, and we're going to be left with a Pythagorean identity. So naturally, we're still looking at, let's see, I factored out a sine to the 4th phi. That became the Pythagorean identity right here. So I have left sine squared phi cosine squared phi. Alright, now what I have here, I can factor out a sine squared phi, and I'm left with a Pythagorean identity for phi again, which means I'm going to be left with just sine squared phi. Nice. Now again, this turns into 4 times the absolute value of sine of phi, But now we then have to go through and figure out, well, is sine going to be positive so that I can drop my absolute values? Well, let's go back to how we defined our parametrization. The way we defined our parametrization was within phi and theta. Phi and theta. So let's go through and let's put some bounds on this now. What is theta bounded by, and what is phi bounded by? And again, it needs to be bounded in order to create this surface that we need to integrate over. So it's a sphere, all right, and it's half of a sphere. In other words, a hemisphere. So what we then need is theta to go from 0 to 2 pi. All right, that's awesome. Now it's only the upper half. Upper half means it's only the top portion, meaning that it's going to be above the x and y plane. So what does that mean for phi? Well, phi, that means it starts at the positive z-axis and it traverses downward to the x and y plane. In other words, it traverses downward to pi halves. So we have our bounds for theta and phi, which means for this piece, we actually get 4 sine of phi. And this is because phi is bounded between 0 and pi halves. 0 and pi halves, sine is always positive within those angle measurements. Nice. So all this work just to set up a just to set up a surface integral. So let's look at that surface integral once again. Here we are. Surface integral, circled it right there. We're going to use that. So we're going to go back down. Here we go. Let's look at that surface integral. Surface integral of z ds is going to be the double integral over some domain that I'm going to be observing, and that's going to be for my function z in terms of my parametrization, where I'm using thetas and phis multiplied by the magnitude of the cross product for theta and phi, and this is going to be dA. Now, how does this all look then? Well, my function z, what was the z value that I chose to parametrize with? My z value that I chose to parametrize with was 2 cosine phi. So that's what I'm using. So double integral, now my function in terms of the parametrization is 2 cosine phi. So that's my z value. Alright, that was my z value there. Now, I'm going to insert my magnitude that I just found, magnitude of the cross product. That magnitude of the cross product is 4 times sine of phi. And that was the magnitude of the cross product. Now I need my differentials. Well, I can do this d theta, d phi, or I can do it d phi, d theta, doesn't matter. Again, we don't need the Jacobian here because we're not changing variables. We're keeping this with the same parametrization that we had. Alright, we're using thetas and phis just because it's a natural extension to parametrize something or this surface in terms of a sphere. Alright, so theta was initially bounded between 0 to 2 pi, there we are, and phi, as we said, was bounded between 0 and pi halves. Which means, here's the integral that we want to now integrate. So we can clean this up just a little bit more. Actually, I'll go over here. Alright, so I'm going to keep this from 0 to pi halves, 0 to 2 pi. Now notice in here I have cosine phi and sine phi. That kind of looks like a double angle mixed with the 2. So I'm only going to factor out the 4, and I'm going to let 2 cosine phi sine phi be that double angle. So that double angle is going to be sine of 2 phi, and this is going to be d theta d phi. So I use that 2, I use that cosine, and I use that 4 to become this double angle. As such. Awesome. Now all we have to do is integrate this, and integrating that should not be too difficult. So take some time and figure out what that integral is, and I'll give you guys the answer in just a bit. Alright, but please go ahead and do it. Put pause on the video. The big bad answer should be 8 pi. Awesome. So this surface integral evaluates to be just 8 pi. Great. So now that we're getting a little bit more into this is going to be awesome. What we now want to do is we now want to start taking this up a notch, just a little bit more, to see how we keep working with these different types of surface integrals. Alright, so here's this example that we're looking at. We're going to evaluate this surface integral where S is going to be the surface whose side is a cylinder, x squared plus y squared is equal to 3, whose bottom is a disk, x squared plus y squared is less than or equal to 3 in the xy plane, and whose top is the plane z is equal to 4 minus y. Alright, so take some time and process this information. And what I'm going to do is I'm really quickly going to draw what I believe my interpretation is of these surfaces. Alright, so here's going to be my interpretation of what we're looking at here. Is that we have this plane. That plane is the top part of this cylinder. Alright, so that plane is z is equal to 4 minus y, and that's this plane right here. We have the disk on the x and y plane, and that disk is down here, and that's my x squared plus y squared is less than or equal to 3. And then I also have this other surface here that goes all the way around. It's a cylinder, and that surface is this x squared plus y squared is equal to 3. So this is my interpretation of what we're looking at. Now we're going to go to GeoGebra and see if this interpretation is correct. Alright, so here I am on GeoGebra for the class, again that multivariable class that I set up on GeoGebra for us. And if you scroll all the way to the bottom here, you're going to see one of the examples that says we have a surface integral example. I'm going to go ahead and click on that to look at this surface integral example. And what I want to do is I want to look at my unbounded surfaces here. Alright, so I have my plane, and that's going to be that blue plane. That plane is going to be z is equal to 4 minus y. Alright, kind of looks like what I kind of drew there. I also have my cylinder, x squared plus y squared is equal to 3, and I should have my disk, which should be right down here. Now, I didn't reflect the disk, or I didn't show the disk, specifically because it's not an unbounded surface. However, when I show my bounded surfaces, you will now see here that I do have all of these surfaces being reflected. So all of these three surfaces, the bottom of the disk, the bottom of that cylinder is this disk, the body of the cylinder is what's reflected here, and then the top part is that plane that was slicing through that cylinder. So when we're looking at that question now says that using the surface integral, I now want to calculate that surface integral for y plus z for all of these three surfaces, because all of these three surfaces make that one big surface that we're looking at, or that we're considering. So this is the figure that we're looking at. Now, when I drew it in class, I believe I kind of drew it like this, alright, just to get that interpretation of what it is that we're looking at. But more precisely, it should be looking more like this. all right, from our typical standard point of view. So now that we got a little bit more familiar with this type of surface, let's go back and let's start dissecting those surfaces a little bit more. All right, so here we are. Now, what I'm going to do here is I'm going to say that we're starting with this surface integral. So the surface integral for y plus z with respect to the surface. Now, we're going to be able to split this surface into 3 different components. So the first one, the first surface, we can go with the plane up here. So we'll say that was, let's say, surface 1. Surface 1 is going to be classified as that top part of the plane. All right, and then we're going to add this to a second surface integral, which in our case is going to be, let's say, the body of the cylinder. So I'm going to call that surface 2. Alright, and I'm going to abbreviate this over here. This is surface 2. Plus the double integral for y plus z with respect to the surface. And this is going to be for my last surface, which is going to be surface 3. And that's what I'm going to classify this surface as, surface 3. Awesome. So now that I'm able to classify all of these different surfaces and observe that this major component, this big S, is going to be comprised of all of these subsurfaces, or minor surfaces, then we're going to go ahead and find the surface integral for each of these values. Alright, so really quickly I'm just going to say surface is equal to, here's S1 union surface 2 union surface 3. There we are. So we then have to think about how we want to do this. Do we want to go with a parametrization? Do we want to use it explicitly? Anything like that, right? We then need to figure out how we're going to go about this. All right, so let's go ahead and let's begin. All right, what we're going to do is we're going to start with one of our cylinders, or sorry, one of our surfaces, and let's just go in order. We're going to start from surface 1, then we'll go to surface 2, surface 3, and then we'll put this all together. So let's go with surface 1. Surface 1, we're looking at z is equal to 4 minus y. All right, so I'm working with this with this surface here. Z is equal to 4 minus y. Now, because I'm given this surface, or this equation of the plane, already in terms of y, what I'm going to do is I'm just going to classify this as my g function in terms of x and y. Alright, now what I'm doing here is I'm using the surface integral explicitly. I am not parametrizing this surface because this surface is a plane. So because it's a plane, I want to just keep that parametrization, or sorry, I want to save that parametrization for different surfaces. So now that I'm looking at this, I want to then go ahead and find the partial derivative with respect to both of these variables that it's defined with. So I'm going to go through and I'm going to find the derivative with respect to x. Now there's no x there, so it's just going to be 0. And the partial derivative with respect to y, which is going to be -1. Alright, and these are I'm gonna hold on to these because, again, these kind of remind you of that gradient that we're gonna need to take the magnitude for. Alright, awesome. So let's start looking at my double integral then. Alright, I'll do this double integral in green. So the double integral over this surface 1 is going to be this y plus z ds, which means we're going to be able to evaluate this over some region, right? Over some region that's going to be reflected onto the domain that we want. All right, now the integrand is y plus z. Perfect. And then we're going to do the magnitude of the gradient here. So the magnitude of the gradient, let's see, g prime of x, that's going to be 0, so it's going to be 0 squared plus 1 squared plus 1. There we are. And this is all going to be dA. Perfect. So our domain, the domain that we're going to be observing for this particular case, the domain, and again, I'm just putting this in quotations because it's really just a region. It's not really the domain that we're looking at. But the region that we're looking at, this domain that's going to be made by this plane for this top of the intersection, is just defined down here, which means my domain is on the x and y plane. Oops. So because it's going to be on the x and y plane, we're going to go through and we're going to define every single component in terms of x's and y's. So what this now tells me for my component here, this is going to be that my double integral over my domain, or over this region, is going to be y plus z value. Well, my z value is this 4 minus y. So I'm going to insert my 4 minus y in for that z value. Perfect. And then I have the square root of 2, and this is going to be dA. Alright, looking good so far. So the y's will cancel then, and we're going to be left with 4 root 2 as a constant, and we're going to integrate over the domain, or over that region, with respect to its area. Awesome. But let's look at the domain. What is the reflection, or in this particular case, what is the projection of this surface here onto the x and y plane? Well, that's just a circle, right? It's just a circular domain, which means we could just integrate using polar coordinates. So we can do polar here, or we can parameterize that domain. However, it's just a circle, which doesn't mean area and an integral of 1. Isn't that just the area of a circle? Sure is. So this is just the area of the circle, which will be pi r. R is the radius. The radius is square root of 3. So pi r squared. There we are. Which then just makes this, what's that going to be, 12 root 2 pi? Nice. So we get 12 root 2 pi for our first surface. Awesome. Now we're going to work on the second surface. And the second surface is going to be the body of that cylinder. So this is where we're going to have to do a lot of the legwork for, all right, because it's not going to be as straightforward. So what we're going to do really quickly is we're going to choose to parameterize this cylinder. Simply because we don't want to use it in explicit form. We don't want to use x squared plus y squared is equal to 3, or sorry, x squared plus y squared is equal to 3. Since it's a cylinder, we want to parameterize using the techniques that we know how to use. So for that one, I'm going to use that parameterization technique. Alright, so surface 2. Here we go. Surface 2. This is a cylinder, which is x squared plus y squared is equal to 3. And let's go through that parameterization. So I'm going to use a parameterization here to say that we're going to parameterize using those cylindrical coordinates. Now, what does that mean for us? Well, that means that x is just going to be r times cosine theta. Y is going to be r sine theta. And z, well, that's just your z component, just z as it is. So, x component here, radii, that was 3. So that's 3 cosine theta. Y is 3 sine theta. And z is just going to be z. Awesome. So we now have this parameterization that we can look at, and it has 2 different variables. The 2 different variables are theta and z. So I'm going to use theta and z. So my parametrization component form looks like this: 3 cosine theta, 3 sine theta, and just z. And now I need to take these partial derivatives so that I can find the cross product. Alright, partial derivative with respect to theta, this is going to be 3 sine theta. This one's going to be 3 cosine theta, and that's going to be 0. And then partial with respect to z, that's going to be 0, 0, and then 1. So 0, 0, 1. Alright, looking pretty good. So we can now take the cross product. So let's go ahead and let's take that cross product now. Oops. I wrote here magnitude, but I'm not doing a magnitude just yet. Cross r of z. Alright, so the first component, that's going to cross out, and then it's going to be 3 cosine theta. There we are. And then the next component, the j component, that's going to cancel out, so it's going to be 3 sine theta. And the last component, z component, should just be 0. Now, when I find the magnitude here, finding the magnitude here, I'm going to square each component, so that's going to be 3 squared times cosine squared plus, 3 squared cosine squared. Oops. My apologies. My apologies. I just realized I made a fudge. My sincerest apologies, everybody. The radius is actually root 3. Derivative there, negative root 3, negative root 3. Alright. Radius here, radius here. There we go, perfect. So now when we take this magnitude, we should just get the Pythagorean identity in here for cosine squared plus sine squared and root 3 as the result. So the magnitude of the cross product is just going to be root 3. Awesome. So now that we have this, let's go through and let's figure out how we're going to set up our surface integral. Alright, so here we go. Surface integral. My initial surface integral for surface 2 is going to be y plus z with respect to ds. Alright, here we go. So, my integral is going to be, my double integral is going to be over some region that I'm looking at. And again, it's going to be this y plus z multiplied by this product here. Alright, and actually I'm going to make my substitutions here. The y value, what was that y component? That y component, whoa, ¿qué pasó? Sorry guys, I hate it when this happens. There we are. So my y component, the y component that I initially chose here was this root 3 sine theta plus the z component. The z component was just z itself. Alright, so that's not too bad. That's my y plus z. Now I need to multiply it by the magnitude of the cross product, and that magnitude of the cross product was just 3. Now this is going to be with respect to the area that we're observing. So let's go through and now let's start classifying what our bounds are going to be. Alright, let's see. So let's see if we can get these bounds here. Square root of 3 sine theta plus z, and this is going to be square root of 3. Now dA, that's going to be the variation over the variables that we chose, which means it's going to be d theta dz. So in this particular case, I'm going to go with, let's say dz, and then we'll go with d theta. Now theta, well, let's figure this out. Theta, for this specific cylindrical surface, theta is going to move, or it's going to traverse all the way around from start to finish, which means it's going from 0 to 2 pi. So theta here, 0 to 2 pi. Z values. So my Z values, my Z heights in this particular case, let's do this in red, my Z heights are going to go from the bottom of that base of the surface to the top part of that surface. So notice they're going from the X and Y plane up until this green surface. So because that's going to be the case, my Z values start at 0, but they go up to the top part of the surface. That top part of the surface was 4 minus Z, but 4 minus Y, but 4 minus Y is really just 4 minus square root of 3 sine theta because of what we chose. Alright, now let me go ahead and highlight that. This piece here is just Z is equal to 4 minus Y. And this piece here was Z is equal to 0. And again, looking at our surface, that's what we were going through. Z is equal to 0 all the way up to Z is equal to 4 minus Y. So now that I have this double integral in terms of my parametrization, I can go through and I can solve this specific integral. Alright, so I'm going to save you the trouble on this integral, and I'm going to tell you that this integral, if you want to keep going, put pause on the video because, hey, spoiler alert's coming up. This answer should be 29 root 3 divided by 2 pi. Nice. So we're able to get this second surface done for that integral. Let's look at the third surface. The third surface is going to be the bottom of that cylindrical disc. Alright, here we go. Surface 3. So here goes surface number 3. Surface number 3, this was our x squared plus y squared is less than or equal to 3. Nice. Alright, so here we go. Alright, let's see what we can do here. So my surface integral at this point in time, well, I have z is equal to 0. That's, since it said it was on the x and y plane, I have z is equal to 0. And if I use z is equal to 0, that's actually going to be really nice in our particular case. Alright, so this is only the disk. This is the bounds, the region that I'm looking at. So what I'm going to do is I'm actually going to use this plane here to see what we can extract. Alright, so let's go through and let's see what we can extract for this particular case. I'm going to label this as my function. Let's go with this function h of xy, because again it's a x and y plane. And since it's the x and y plane, then naturally the x and y plane has an equation of z is equal to 0. So if I take the partial derivatives here for h of x, then I get 0. H sub y, that's going to get me 0. Awesome. So when I look at my surface integral, and this again for y plus z ds, I'm going to be looking at integrating over some region D, and this is going to be for y plus z. So y plus z, but z is equal to 0 in this particular case, so that's not too bad. We're not parametrizing here because again we're only looking at a plane. It does have a bound, and we will consider those bounds in just a bit. That's going to come with this domain or with this region. So for now I'm still working on this plane. Alright, now I need the magnitude of this gradient, so that's going to be 0 squared plus 0 squared plus 1. There we are. And this is going to be with respect to some area. This is now going to tell me that I'm looking at the double integral over some region for y. That's going to be the square root of 1, so that's just 1 dA. But now, what region are we looking at? So the region D that we're looking at is this x squared plus y squared is less than or equal to 3. Which means we're going to be integrating over this domain, which is we're going to be integrating over this circular domain, which means we can use polar coordinates. So what I'm going to do here is I'm going to take this here, this double integral over this region D, and I'm going to integrate y with respect to dA, but the region is in x and y form, and I'm going to switch it over to polar. Alright, so if I switch this to polar, then my y coordinate is just going to be r sine theta. Again, that's my y coordinate there. My dA, well, I need my Jacobian here, r dr d theta. Alright, not too bad. Now my limits of integration. Theta for this disk goes from 0 to 2 pi. And the radius is going to go from 0 to square root of 3. Here we are. Which means what we get here is going to be the integral from 0 to 2 pi, from 0 to root 3, and this is going to be r squared sine theta dr d theta. Now this should be a nice integral to evaluate. Alright, it's not going to be a bad integral to evaluate. So if you want to evaluate it, go ahead and spend some time evaluating this. Put pause on the video and go ahead and do that. But I will tell you, spoiler alert, it's just 0. So what we want now is we want to look at that integration that we saw here. So what I'm going to do is I'm going to just take this here, and I'm going to move it down below. So let's go ahead and let's copy that. And let's start looking at that here. There we are. So my surface integral so far, now my first surface integral, that was this 12 root 2 pi. That was that first surface integral. Second surface integral was 29 root 3 divided by 2 pi. And that third surface integral was just 0. So what do we get as our final answer? Well, our final answer for that surface integral that's made up of those three surfaces is going to be pi halves multiplied by 29 root 3 plus 24 root 2. And there we have it. This is our final answer. Alright, so there is a lot of work that goes into this type of problem, as you can see here. Alright, as we can see here again, let me zoom out just a little bit more. There we go. As you can see here, a lot of work must go into this, and we always have to identify how many surfaces does the initial surface, how many surfaces is the initial surface comprised of. As soon as we answer that question, then the second question now becomes each individual surface. Do we parameterize it, or do we work with it explicitly? If we parameterize it, great, then go ahead and do the parametric work for that. If you don't parameterize it, again, okay, great, go through the work to find out what that surface integral will be. Alright, so this is the method of surface integrals that we look at. Now, let's go ahead and let's now start looking at what's going to happen if we take one of these surfaces and we put it into a vector field. Alright, so I'm going to give you a quick example of that. Alright, so here's the example that I kind of want to view here. And if you remember from the very beginning of this section, or from the very beginning of this video, we looked at this example without the vector field. I gave you this example and said, hey, we have some surface and we're going to want to do these surface integrals. But now that we know about these surface integrals, what's going to happen if we put this surface into a vector field? Right? We then want to know how this vector field is affecting this surface or how this vector field is going to affect this surface. So we then have to then start analyzing what are the different components that are affecting this surface and in what way are they affecting it. And in that sense, we now get to talk about flux. Alright, so flux is just, in a nutshell, trying to figure out how much of a certain object or a certain quantity is passing through a given surface. Alright, so let's go back and let's start getting a definition for how we're working with this flux. Alright, so here's the theorem that we work with. It says if F is a continuous vector field defined on an oriented surface S. Again, we need to find an orientation of the surface, that way we can have a normal vector that we then identify with that oriented surface. And this says with unit normal vector n. Then the surface integral of F over S is given by this surface integral. And again, I want you to identify the notation that we're using. We're using this notation here that says that I want to find this flux, right, or this surface integral over this vector field, over the surface S that's being submerged in this vector field. So we have a vector field and we're going to have a surface here that's going to act as a vector as well. So we have to be very, very careful with this notation. When we do this, we have this surface integral that we can evaluate, and this surface integral is the actual definition that we looked at from the very beginning of this section, where we look at some function with some normal vector. But in this particular case, since a vector field is typically defined in vector component form, we're going to have a vector dot product with another vector, which means we're going to get a scalar, we're going to get a real valued scalar function as a result that we need to integrate. Now, the integral is oftentimes called the flux of F across S. Now, the alternative form. The alternative form is going to be, if we can parameterize a surface, then we can use a cross product of those partial derivatives. And again, that still holds with this normal component that we're looking at. If we were looking at a normal component and we use the unit normal vector, well then it would turn into the exact same definition that we were using before. So, one of the items that we need to always consider is positive orientation. So positive orientation for, let's say, a surface S is when the normal vector is pointed away from the bounded region. Now, in order to satisfy this, we are going to need to identify every single surface that we're trying to calculate the flux for. Once we're able to calculate that, or once we're able to visualize that surface, then we're going to be able to extract what is that normal vector that we are then looking for. All right, so let's go through, and we are going to do an example in just a little bit. All right, so here's the example that we're working on. We're going to evaluate the flux for this vector field across the surface S, and the surface is going to be this paraboloid given by y is equal to x squared plus z squared, where it's going to be bounded by 0 and 1. So this paraboloid bounded by 0 and 1, and then it's also going to have a bounding of this disk x plus z squared, which is less than or equal to 1 at y is equal to 1. And then we're going to assume that S has positive orientation. Alright, so let me give you again a quick sketch, a quick interpretation of what I think it looks like, and then we'll go to GeoGebra and we'll verify if it is in fact that's what it looks like. So paraboloid, this paraboloid is going to open along the y-axis. So let's look at this paraboloid here. So I'm going to go this way. I'm going to come back down. Looks like this. Yeah, that looks kind of crabby. This is my interpretation of it, where we have two different surfaces. One of the surface is this face here, and that surface has, let's see, x squared plus z squared, which is less than or equal to 1, and this is at y is equal to 1. And then we also have this other surface out here. So this other surface is given by the paraboloid y is equal to x squared plus z squared, and this is also going to be bounded by 0 and 1 for my y values. So let's go to GeoGebra really quick and see if we can get this to pop out. Alright, so here we are, we're on my GeoGebra account, and I'm going to go over here to my flux example. So on this flux example is where I've created this surface here, and that surface again looks like that surface that I was trying to portray there, where we have this paraboloid here. Alright, that paraboloid's opening along the y-axis, and then we also have this disc that is bounding that paraboloid towards the end, towards that opening. Alright, now one of the other things that I also have that I again need to consider here is going to be a normal vector. Alright, and I do have on here this vector. Wow, GeoGebra is just doing all this funky stuff today. Alright, let's see if I can reorient this. There we go. Alright, so once we're looking at this, again, we need to consider this normal vector, and again, it's going to have to be a normal vector to that surface. So as we start moving this vector, this vector should always be able to stay normal to this surface that we're observing here. Now, the big question is going to be, how do we get that normal vector? Alright, now that is going to be the big question, and we'll get to that in a bit. But one of the other questions, or one of the other observations, is that this surface, this total surface, is made up of two different surfaces. One with this blue surface, again being that paraboloid, and the other being this purple surface here, which being that disc that was given to us. So now that we get to see how this is oriented and how it is portrayed, let's go through and let's make some calculations for our surface. Alright, so in order for us to do this calculation, we're going to have to do, again, two different types of integrals that we're going to have to work with. So let's go through and let's start setting those up. Alright, this is going to have two different surfaces. One of them is going to be surface 1, which I'll do in green, and then the other one is going to be surface 2, which I'm going to denote in orange, surface 2. And again, just that observation that the surface, the initial surface that we're looking at, is going to be a surface that's made between two different ones, which we'll call surface 1 and then surface 2. Alright, so let's work with surface 1 really quick. Alright, surface 1. So surface 1 is this x squared plus z squared less than or equal to 1 at y is equal to 1. Now, this is going to be a really nice surface to work with. So this is surface 1. And it's a really nice surface to work with because the normal vector that we can extract is going to be a really, really nice normal vector. Let's see here, surface 1 here. There we are. Now, the vector field that we're looking at is this vector field right up here, so that's going to be y in the j component minus z in the k component, and we need to dot this. We need to find the dot product between this vector field and the normal vector to that specific surface. All right, that's according to the definition that we have right over here that says we need to take the we need to take the continuous vector field and the dot product between the normal vector of that surface. So the surface is this green piece here, or that green face. Now its normal vector is just going to be pointed outward, and it's going to be perpendicular to it. Now, which vector does that? And I'll go back to GeoGebra to show you a little bit more cleanly. All right, here we are in GeoGebra. So which vector is normal to this purple surface here? Notice it's very, very nice and straightforward. There's actually a really nice vector here. It's the j component. The j component is the unit basis vector. The unit basis vector j is the vector that is normal to this purple surface. So we can just use that as our normal vector. So coming over here, my normal vector, the normal vector that I want to use is just going to be the normal vector that's in the j component. All right, that's not too bad. And then again, this is going to be with respect to the surface. All right, that's looking pretty good now. Now that we have this, we can go through and we can now start setting this up using our forms with double integrals. So let's find that dot product here. That dot product is just going to be y. All right, there is no z component there, so it's just y ds. All right, looking pretty good so far. Very nice. All right, so now we can just go through and we can start evaluating this. All right, so over some domain, over some region, the y value, what are we using for the y value? Well, the y component is just y is equal to 1. So that's just y is equal to 1, and this is going to be with respect to some area. So what I'm using here is I'm using the definition for line integrals. All right, and what did I use from here to here? I used the definition for flux. So understanding that, I took this definition for flux, I embedded my components that I was looking at for this specific surface. Once I did that, I was then able to use this definition for line integrals, which means now I'm just trying to calculate an area here, because again my integrand is 1. I'm trying to calculate my area, and that's going to be the area for this disk. Well, area for the disk, that's not too bad, because again it's just a circular disk, so that means this is just going to be pi times r, radius. Well, what was that radius? That radius was 1 squared, which is just pi. Nice. So there's surface 1. Surface 2. Surface 2 is going to be a little bit more difficult, but we'll work through it. All right, so let's start off surface 2 on this side over here. So we're going to go with surface number 2. And surface number 2, as we can see over here, this was y is equal to x squared plus z squared with y being bounded between 0 and 1. All right, so we have a few things to do here. We need to find a normal vector. All right, so we got to try to find a normal vector here. Now, the nice part about this is that we can go through without the parametrization techniques that we have here, and everything will still work out. All right, so that's what we're going to work on here, is we're going to work on trying to extract what we have. All right, so let's go through here. All right, here we go. So this is going to be the double integral over this region, which is going to be region 2, surface 2, with respect to ds. All right, looking good so far. Now what I'm going to have here is I'm going to have this double integral over my region D. And again, I'm going to bypass this definition for line integrals really quick, and I'm going to say, okay, well, if I can go here, then I can go here, which means I'm going to end up here regardless. So I'm going to bypass this intermediate step. So I'm going to go over through, and again, bypassing that step leads me straight to that surface integral definition. My apologies for surface integrals. There we are. So definition for surface integrals, that's what I use. So I'm going to bypass that whole definition for flux, and I'm going to go straight to embedding the definition for surface integrals. So once I'm able to do this, I'm then going to get my function here, which is going to be my vector field function, which was that y in the j component minus z in the k component. And I'm going to take the dot product between the normal vector that I'm going to find. Now the normal vector, what I'm going to do is I'm going to make this normal vector a unit normal vector. Alright, so making this a unit normal vector, I'm going to need some sort of gradient, and I'm going to divide by the magnitude of that gradient. My integrand here, or my differential then, will account for that in saying, hey, this is going to be the magnitude of my gradient with respect to the area. And again, remember, that was the definition for surface integrals or for line integrals that we worked with. So in this whole process, I now need to figure out what is this normal component, or in other words, what is the gradient to this specific surface. So that's what we need here. We need to find that gradient. In order to find that gradient, we're going to need to consider this specific function being a function with 3 variables. That way, once we find this gradient, we're going to find this gradient and it's going to be orthogonal to this specific surface. So, what I'm going to do here is I'm going to say let x squared plus z squared minus y equal 0, and in turn this is going to be x squared plus z squared minus y, which is going to be this function f of x y z. So when I try to find the gradient here, finding the gradient here will then again be orthogonal to this specific surface that I started with. So let's go through and let's find that gradient then. So gradient up top, all right, that's going to be partial with respect to x, so that's just 2x, partial with respect to y, that's going to be -1, and then partial with respect to z, that's going to be 2z, divided by its magnitude. Now notice, I don't need to divide by its magnitude because, again, when I divide by its magnitude, it's actually going to cancel out with that magnitude that I needed to have at this point in time. So when I do this, this is going to be, again, that was 2x, -1, and then 2z. There we are. And this is with respect to dA. Alright, that doesn't look too bad. Which is just the integral over some region. And let's see, let's start taking our components now, our dot product. So this is going to be -y. Alright, that times that. Minus that times that. So -2z squared is what I end up with here that we need to integrate. Awesome. So really quickly, I'm going to go back to GeoGebra really quick, and I'm going to show you why it is that we cannot stop here just yet. Alright, so far we found this normal component, which was really nice, and the reason I say that we can't stop there just yet is because we have a function in terms of y's and z's. However, if I take this, if I take this specific domain or this specific region and put this region or project this region onto a, let's say, domain, then my domain is going to be back here, which is the x and z components. It has no y's embedded in it. So because of that, I need to go through and I need to restructure my integrand to reflect that my domain is going to be in the y and z component, and it will have no y components to it. So here we are. Now again, we don't want any y components here, because again, our domain, our region that we're looking at, region is projected, whoa, cheese and crackers. All right, here we go. Whew. Alright, so I'm going to say the region is projected onto the x and z plane. Alright, which means again we have a y value there that we can't have the y value there for. So I'm going to insert my y value. My y value is actually x squared plus z squared. And then I have minus 2z squared, and that's dA. Which means this is my double integral over that region for, let's say, negative x squared. And that's going to be negative and negative, so that's going to be minus 3z squared. And that's going to be with respect to its area. So now all we have to do then is figure out, well, once we project this region onto the x and z plane, what type of region do we get? Well, projecting this orange region onto the x and z plane, we just get a circular disk. So that must mean that when we want to evaluate this, all we need to do is integrate over that disk in polar coordinates. Theta goes from 0 to 2 pi, radius is going to go from 0 to 1, because again, remember, your y values were bounded between 0 and 1. The x component, well, I can consider my x component as r cosine theta squared minus 3, the z component, that's going to be r sine theta squared, and then I still need here my r dr d theta. D theta, there we are. Again, because we went from Cartesian over to polar coordinates. Alright, let's see if we can simplify this just a little bit more. That way we can definitely extract the equation that we are supposed to be integrating. So in here, let's see, I have the integral from 0 to 2 pi, the integral from 0 to 1. Let's distribute the r. So if I distribute the r here, or if, let's say I factor the r, I'm going to have negative r, that's going to be cubed, multiplied by cosine squared theta minus, or in that case plus, because I factored out the negative, plus 3 sine squared, oops, I forgot that 3, plus 3 sine squared theta, and this is going to be dr d theta. So all I need to do here is evaluate this integral and we'll have it. Alright, if you want to evaluate the integral, by all means go ahead and do so. However, I'm not going to evaluate this integral directly just yet. I'm going to wait for you guys to do that. Alright, still waiting. Alright, so here we go. So once we're able to extract this, because it's negative, and once you do your calculations, you're going to get negative pi as your final answer. Alright, so now that we've calculated these two integrals, what I'm going to do here is I'm going to start summarizing this. And let's go ahead and copy this. And let's copy it here. There we are. So now that we got this, we can say, well, the first integral, the first double integral for the flux, we were able to get pi here, and that was the one in green here. So we were able to get pi plus the double integral for the second integral, which was negative pi. There we are, which means we get a total flux of 0. And that is how we work with these surface integrals and how we work with this flux concept for these surface integrals. So I hope you all enjoyed this lesson, and I will see you all for the next lesson, which will be on Stokes' theorem, and then hopefully shortly after that the divergence theorem, and that will end the course. So I will see you then, and stay tuned.